our calendar today, I wanted to show you the full one because for some reason, I don't know, one of the pictures doesn't show up, so I'm going to show it to you here. So I wanted to get in the holiday spirit, so hopefully you get in the holiday spirit as well this weekend. Probably some of you already have your holiday decorations up. We do not yet. Well, I should say I still have up my Halloween one, so I've got to change that. Anyway, we're going to talk about something called triboluminescence. We're going to talk about light and color and the electromagnetic radiation spectrum and how the heck all of that is related to the atom, or at least get started on it. So, yeah, I hope you're having a good day. In your classwork feed, you should have gotten this document. Again, this is just a note sheet. It is not anything to turn in. It's just to help you remember what we talked about. I did put in the links to different videos. I'm only going to show one of them completely and part of 2 others. So if you want to look at them more, you can. But our focus is going to be on light and color today. And again, you're probably better off taking notes on your own paper rather than trying to pull that document up and type as we go. So that's my advice to you. You can do what you want, obviously. So again, as usual, I'm skipping around the book. So I'm at the end of chapter 5. I think it's important to have this background information because it's more chronological, actually. We noticed all this stuff that we documented. We scientists documented all this stuff before we saw the link between it and atomic structure. So I think you should have that background knowledge so when we talk about atomic structure and spectral lines, you understand where all this stuff came from. So all of us have seen neon signs before. And neon signs, what most people don't realize is they are actually originally filled with neon gas. And so even though they come in a variety of colors, what most people don't realize is neon gas, which to your eyeballs normally is colorless. When you run an electric current through it, it turns this crazy intense red color. And normally I'd show you that in the classroom, but we can't. So originally the neon signs were glass tubes filled with neon gas that would glow red. And now, of course, the glass in some of them isn't glass at all, it's plastic, but in some of them they have colored glass. But originally, the bright red signs came from the neon gas in them. Different elements glow different colors when you heat them up. Fluorescent lights, the tube lights that you probably have in your garage or you've seen at school and stuff, they're filled with mercury, a little bit, not a lot, just a little tiny bit of mercury. And so compact fluorescent lights as well. And that mercury, the characteristic of mercury when it glows, it's a shiny silver metal, but the gas, when it's electrified, glows this cool white color. So anyway, just a little background on some things you may not know about. This gentleman, we'll watch a little bit of this clip, pretty crazy attire, but you know, late 1500s, early 1600s, that's how they dressed in England. People with money anyway had these big weird collars, and he was a man of nobility, so he had this weird hat. Anyhow, Sir Francis Bacon is considered by many to be the first person to say, you want to be a scientist, you got to do experiments, okay? And instead of just listening to people like Aristotle who thought things and didn't do any testing. So I'm going to introduce triboluminescence with this video, and we're not going to watch the whole thing, but you can go back and look at it later. Triboluminescence is a phenomenon that actually is common. Even Band-Aids and Scotch tape, if you can photograph them in the right light, you will see this weird experience. All of us have experienced static electricity before, and many of you know that lightning is a scaled up version of static electricity. As things rub against each other, whether it's your foot on the carpet or clouds in the atmosphere, that rubbing process knocks electrons off of things, and you can get a buildup of negative charge on one side and a positive charge on the other. And then, of course, everything wants to go to neutral, so the charges jump. That's when you see lightning. That's when you get zapped by the static electricity. And tribo is Greek or Latin for rubbing things together. Lumen has to do with light, so it's the creation of light by rubbing objects together. So I'll let him talk for just a minute. We're not going to watch this whole thing, but like I said, you can watch it later.
In 1620, Francis Bacon wrote a book arguing that scientists should trust experiments instead of old philosophers. And in that book, he somehow found the time to mention that sugar emits light when you crush it. This non sequitur is the first documentation of a phenomenon we now call triboluminescence. Today, we know that his sugar wasn't special. Tons of different crystals shine under stress, like those minty lifesavers candies that spark blue when you chew them. And modern scientists are researching ways of working stuff that glows like this into all sorts of futuristic devices. Although they can't quite agree why it happens in the first place. Triboluminescence, also called mechanoluminescence, is the release of some sort of light from some sort of crystal because of some sort of physical stress. And if
chop this head off. What's going on in that segment there is you're watching someone, and they're using a good camera, better than the one I have, strike two rocks together, two pieces of river rock, quartz rock, and the fractures, the cracks in that rock actually create the gap that electrons go over. And I actually have some quartz rock that I normally would show you, but I'm going to let him finish up and then I'll show you another little.
That definition sounds pretty wishy-washy to you. That's honestly because it is. The most famous kind of triboluminescence is from wintergreen lifesavers. If you take one into a dark bathroom and bite down on it, crushing the sugar crystals inside, you can often see a little flash of blue light in the mirror. But some crystals shine when they're fresh.
So, normally I would also give you a wintergreen lifesaver, and you would go back to back of the room and we turn out the lights and you chomp on them. So you can still do this on your own. You can go buy some. And I happen to like the taste of them. So that menthol taste is methyl salicylate. And that oil of wintergreen is what helps boost the sugar electrons to a high enough level. So when you crush the sugar, sugar's a crystal, when you crush the sugar, of course, candy is mostly sugar, right? You can actually see a blue light. So you have to do bad manners. You have to chomp with your mouth open at the mirror. But if you gotta give your eyeballs a chance to dark acclimate also, just like when you're trying to see stars and stuff. So tonight, if you get some winto, it's a play on words, right? Winter instead of winto green. Lifesavers, those little round donut candies, chomp on it, and you might very well see that spark. You can barely see it. There's a couple people on the internet that have better images than that one, but some people see it as a green color, and some people see it as blue. It just depends on the quantity and location of cones in your retina, but it's fun to do and fun to show other people. I hope some of you have seen that before. This is a piece of rose quartz with a stationary drill acting on it. So I just want to show you this real quick. I actually have a piece of rose quartz that does that. So there's lots of fractures in the rock. You can't see them, all exactly, but most quartz crystals, you can see some of them. And you can pick up these rocks probably around town, around your house if you have property. River rocks are going to be mostly quartz anyway. So this drill is rubbing on the rock, and those sparks you see are actually light inside the rock. It's actually like static electricity inside the rock. And so he said that we don't really understand how this works. Yeah, in some things, we know it's all about electrons. So I guess the exact pathway for it to happen, maybe not clear, but we do know it's the electron. So the blue color is shorter wavelength light, closer to ultraviolet. So that means it has more energy. The reddish, orangish color from the rocks is longer wavelength and lower energy. Some of you may have seen flame tests before. And my husband does this for his students at the Solveville, right there. But different metals change colors when they're heated, whether it's with electric current or with a flame. Those flames are more fun because we're all pyros at heart, right? But each of these colors happens because there's a different metal present. And because I've done this before, I know that the yellow color is probably sodium, and I know that this color is probably from calcium, and I know that this color is probably from strontium, and this one from lithium, and this one, which you can barely see, that faint violet color is probably potassium. And if we were in the classroom again, we'd be learning how to light our burners and do this, but we'll have to wait until another day, hopefully in January. Okay, so again, metals are in compounds, whether you know it or not. And so sodium chloride, sodium's a metal, chlorine's a non-metal. Together they make table salt, but there's lots of salts. That's a generic term to chemists, where you take any metal, it doesn't have to be sodium, it could be calcium, it could be lithium, whatever, and you put it together with something else. And you remember, I hope, the copper chloride crystals we looked at earlier this year. We put them into water. They had a greenish color. Well, it turns out when you heat copper in a flame, its ions also give off that blue-green color. And anytime, so if you've ever taken, say, Christmas wrapping paper and put it into your fireplace, or maybe you had a fire pit and you put magazines or advertisements, you know, with all the colors on them, the pigments in those inks will often give you colors as well. Okay. This, I'm not going to play this video, but a gentleman does this. This is like what my husband does. He takes different kinds of salts and puts them in alcohol and then lights them. And it's quite entertaining. And of course, that is the basis for the firework industry too. Fireworks have different colors because mixed in with the explosive powder stuff are different metals that when they're heated or excited, their electrons get excited, then you get those different colors. All right, so what is color? What is light anyway? Well, Isaac Newton proved that the white light that we see that doesn't look like anything is actually composed of all the colors possible. And again, raindrops act like prisms. This is a prism picture representation, a triangle. The different wavelengths of light will separate, refract differently. And when you see a rainbow, that's what you're seeing. And sunlight is what we call a continuous spectrum. It has all the colors in it, and they don't have any black lines or breaks in them like this. It's every color possible that you can begin to imagine. Of course, it's a problem if you're colorblind to try and do this kind of work, so you may or may not be suited for it. You probably studied color blindness when you did biology, and you know that males are more likely to be colorblind than females, although females can be too. Also, red-green color blindness is most common. Some people have yellow-blue color blindness, and some people are totally colorblind, which is very unusual, but it happens to some people. And usually every year I have at least one person who's colorblind of some degree in my classes. You probably, some people don't even know about it until it's brought up in a science class, because you kind of make adjustments. You assume a certain color is named a certain thing. It's how you perceive it. It may not be how everybody else perceives it. An interesting story, John Dalton, the guy that brought atoms to modern times, that matter's made of some little smallest piece. He was actually colorblind, and he didn't realize it until his 30s, because, you know, he got along fine with everything. But at some event he went to, there were colored roses at the center of the table. When it got dark and there was just candlelight, they looked a different color. He started asking people, wow, did you know the roses changed colors? And they're like, no, they didn't. They're still the same color. Anyway, he was sharing that information with his brother via a letter, and turns out both of them are colorblind. So kind of interesting, heredity. All right, so this is 25. Many people can see that. This one's a little harder, depending on if you have color blindness or not. That's a 6, a 45, and an 8. I don't know if there's any of you that can't see any of those, but it will be hard to do spectroscopy if you are, just FYI. Yesterday, our conversation about what electrons were. Are they particles? Are they waves? Well, that same kind of confusion was circulating around in the 1600s about light. Is it a particle or is it a wave? And Isaac Newton thought it was matter, a particle. Okay, and Christian Huygens, I believe he was Dutch, proposed that it was a wave. And there were different experiments that you could prove either particle or wave. The most famous experiment in the turn of the 19th century, Thomas Young proved with his double slit experiment the wave nature of light. And so we're going to focus on waves. And so this is an experiment you will probably do if you take college physics. A light source emits light. Light travels in waves. How do we know that? Well, if you pass the light through two slits at some distance apart, the waves propagate again, and then they start to overlap each other and interfere with each other. And there's something called destructive interference and constructive interference. Sometimes if it's constructive, it makes it bigger. If it's destructive, it cancels it out. And you can see this with water waves as well. At any rate, he proved that this that light behaved like waves. So there are others experiments that prove that light behaves like a particle, and that's the dilemma we still kind of face. How does that happen with light? How does that happen with electrons? We know electrons are particles, but they also have wave-like characteristics. So that's kind of the link between all this. So waves, let's talk about them. There's some terminology you need to know. And it's on the sheet. I have this diagram on the sheet. The top of a wave, just like an ocean wave, the top of a wave of light is a crest. The bottom of the wave of light is called the trough. You notice there's a blue line in the middle. That median line is an imaginary, like equator. Okay, so the highest point the wave reaches above that, and the lowest point is known as, well, I'll get to it in a minute, the amplitude. Where the wave crosses that middle line is called a node. And again, the amplitude is how high above that imaginary middle point you reach. With sound waves, that's directly correlated with volume. With light waves, it's more correlated with brightness. Long wavelengths have greater distance between crests. Short wavelengths have a less distance between crests. So crest to crest is called the wavelength, and we abbreviate the wavelength with the Greek letter lambda, L for length. That doesn't look like an English L, I know that. It looks like an upside down Y, but that is, it's kind of like a little I don't know, a little curly Q with a leg. Okay, so that's lambda. You need to know that symbol, just like you know pi and delta. We measure wavelength in meters in the range of wavelengths that are visible to your eyeballs. They're in nanometers of billions of meters. Another part of light is the frequency of the waves. How many of them go by in a certain amount of time? And so if we imagine this blue line to represent a second, an interval of 1 second, you'll notice there's one wave, 1, 2, 3 nodes, right? From this point on this wave to the same point on the next wave, that's one wavelength. And then there's a second wavelength, right? And we represent frequency with the letter nu, and it doesn't look anything like an N. I understand that, but nu is the Greek letter for number, NU and number, of wave cycles to go past a point in a given unit of time. My dog's gonna bark here any second when she wakes up. Yeah, how about that? Okay, the daughter's home and the dog didn't bark. It's amazing. So frequency is nu, and you do have to know how to write that. It just looks like a V, but that just happens to be how this font shows up. So the unit for frequency is the hertz, like the spelled like the rental car company, no relation. Well, maybe there's a related, I don't know. He's a German physicist. So hertz is cycles per second or number of waves per second. So on the left-hand one, we've got 2 hertz, if that blue line is 1 second. On the right hand, we've got 1 wave, 2 waves, 3 waves, 4 waves, 5 waves, 6.5 waves. You can have fractions of waves. And so you may know that radio stations have numbers. Those numbers correspond to kilohertz and megahertz on the frequencies. To tune into things, you have to be in the right bandwidth to get it. Okay. All right, light. Light and the wavelength and frequency of light, or any part. Most of us think of light like the lights in our house, but to a physicist or to a chemist, any part of the electromagnetic spectrum is considered light. So wavelength and frequency are inversely proportional. As the wavelength gets longer, the number of waves per second, the frequency gets shorter. As the wavelength gets shorter, the number of waves per second gets bigger. One goes up, the other goes down, one goes down, the other goes up. That's an inverse proportionality and inverse relationship, indirectly related, however you want to phrase it. Okay. And we'll find out next week that frequency is directly related to energy. Higher frequency, higher energy. That's why gamma rays and X-rays are bad for you. All right, so this formula, make sure you get this down. C equals lambda nu. C is the speed of light. And unfortunately, there's lots, it's a constant, but it's not C for constant. It's the speed of light. And so it's also in Einstein's E equals mc squared, right? Lambda is wavelength, nu is frequency. Multiply those together and you get the speed of light. Well, this is a constant. So that means this number never changes. It's always, for our purposes, we're going to use 3.00 times 10 to the 8th meters per second. A little bit different when you have an extra sig fig, but this is good enough. Okay, so if we can measure the wavelength of the light, we can calculate its frequency, right? You just rearrange little baby algebra and solve for nu. So again, wavelength is lambda, nu is frequency. And these type of problems, we're going to work on some of these next week as well. What's the frequency of radiation with a wavelength of 5 times 10 to the minus 8 meters? Well, you got to know your equations, like saying what's the density if you've got mass and volume, or if you know the density and you know the volume, can you solve for mass? Of course. So we just do a little rearranging, divide both sides by lambda. The value for the speed of light doesn't change. That goes in the numerator. The wavelength is whatever you measure. And then you just do the math. And that is as easy as it gets. You just have to remember how to do scientific notation. So we'll go over that again, like I said, next week. You don't have a scale, but I will give you a sheet next week where you can look on it to find out what part of the spectrum it's in. Right, again, the visible spectrum is a very tiny sliver of the entire electromagnetic radiation spectrum. Everything from wavelengths that are miles long, those are radio waves, to gamma rays that are fractions of millimeters long. Your eyeballs see this continuum, but it's a really small segment of all the kinds of energy traveling in waves at the speed of light that are out there. And so we're gonna watch this really quick for 5 minutes, and then hopefully you'll learn a little something more. This is by NASA.
Something surrounds you, bombards you, some of which you can't see, touch, or even feel. Every day, everywhere you go. It is odorless and tasteless, yet you use it and depend on it every hour of every day. Without it, the world you know could not exist. What is it? Electromagnetic radiation. These waves spread across a spectrum from very short gamma rays to X-rays, ultraviolet rays, visible light waves, even longer infrared waves, microwaves, to radio waves, which can measure longer than a mountain range. This spectrum is the foundation of the information age and of our modern world. Your radio, remote control, text message, television, microwave oven, even a doctor's X-ray, all depend on waves within the electromagnetic spectrum. Electromagnetic waves, or EM waves, are similar to ocean waves in that both are energy waves. They transmit energy. EM waves are produced by the vibration of charged particles and have electrical and magnetic properties. But unlike ocean waves that require water, EM waves travel through the vacuum of space at the constant speed of light. EM waves have crests and troughs like ocean waves. The distance between crests is the wavelength. While some EM wavelengths are very long and are measured in meters, many are tiny and are measured in billions of a meter, nanometers. The number of these crests that pass a given point within 1 second is described as the frequency of the wave. One wave, or cycle, per second is called a hertz. Long EM waves, such as radio waves, have the lowest frequency and carry less energy. Adding energy increases the frequency of the wave and makes the wavelength shorter. Gamma rays are the shortest, highest energy waves in the spectrum. So, as you sit watching TV, not only are there visible light waves from the TV striking your eyes, but also radio waves transmitting from a nearby station, and microwaves carrying cell phone calls and text messages, and waves from your neighbor's Wi-Fi, and GPS units in the cars driving by. There is a chaos of waves from all across the spectrum passing through your room right now. With all these waves around you, how can you possibly watch your TV show? Similar to tuning a radio to a specific radio station, our eyes are tuned to a specific region of the EM spectrum and can detect energy with wavelengths from 400 to 700 nanometers, the visible light region of the spectrum. Objects appear to have color
because EM waves interact with their molecules. Some wavelengths in the visible spectrum are reflected, and other wavelengths are absorbed. This leaf looks green because EM waves interact with the chlorophyll molecules. Waves between 492 and 577 nanometers in length are reflected, and our eye interprets this as the leaf being green. Our eyes see the leaf as green, but cannot tell us anything about how the leaf reflects ultraviolet, microwave, or infrared waves. To learn more about the world around us, scientists and engineers have devised ways to enable us to see beyond that sliver of the EM spectrum called visible light. Data from multiple wavelengths help scientists study all kinds of amazing phenomena on Earth, from seasonal change to specific habitats. Everything around us emits, reflects, and absorbs EM radiation differently based on its composition. A graph showing these interactions across a region of the EM spectrum is called a spectral signature. Characteristic patterns, like fingerprints within the spectra, allow astronomers to identify an object's chemical composition and to determine such physical properties as temperature and density. NASA's Spitzer Space Telescope observed the presence of water and organic molecules in a galaxy 3.2 billion light-years away. Viewing our sun in multiple wavelengths with the SOHO satellite allows scientists to study and understand sunspots that are associated with solar flares and eruptions harmful to satellites, astronauts, and communications here on Earth. We are constantly learning more about our world and universe by taking advantage of the unique information contained in the different waves across the EM spectrum.
And if for some reason your internet was glitchy during that, I have the link on the note sheet. So again, electromagnetic radiation is everywhere. And it turns out that you're using it all the time, whether you know it or not. Night vision goggles, most of us don't have those, but some of you do, or scopes for hunting. Ultraviolet light. Who knew you can buy ultraviolet lights to try and find out if where your cat is peeing in your house. Also, living scorpions will glow with ultraviolet light. This is Rontgen's wife's hand again, and then gamma rays. So again, we're going from the longest wavelengths of radio to the shortest gamma, from the lowest frequency to the highest. Okay. Also, danger. High frequency means high energy, as we'll find out more next week. And then this is a picture of a spectroscope. This is the type that we have, this old one that can be used to use spectral lines, which is why we're going over all this color stuff and light stuff, so we can talk about the spectral lines that electrons give off and how we use that to figure out the structure of the atom. So I want to let you get going and answer any